English for Engineering.
Tiếng Anh ngành kỹ thuật.
9.1.
With the aerodynamics, there are three development tools available to us. The first is CFD software, Computational Fluid Dynamics. With that, the tests would obviously be virtual, based on a computer model. The second option is to go into a wind tunnel with a scale model or a full-size mock-up. In either case, we'd probably need to use a tunnel with a rolling road.
Would that be necessary?
Well, the thing is, the wheels generate a lot of turbulence when they're spinning, so to simulate that, you need a rolling road.
Yes, I know, but if we go for a bodywork design where the wheels are mostly enclosed, which is likely, would that be an issue?
Possibly not. It depends how fully enclosed they are.
Okay, I'm just raising the question.
Sure, it's something we can look at. The third option, then, is field testing, actually running the prototype outside on a runway or somewhere. So we can use these tools in isolation or as a combination. The question is, how can we gather as much data as possible with the limited budget we have?
Well, we need to bear in mind that the problem with aero is that it's not just about data gathering. You also have to validate the data. CFD and wind tunnels are not 100% reliable. The acid test only comes when you try out a full-scale prototype in real conditions. We need to make sure that everything is tried and tested outside with a full-scale trial run.
Yeah, but let's not forget we're designing a car that does 100 kilometers an hour. It's not a supersonic aircraft. The aero is not going to be that critical.
Plus, with changeable weather, it's not easy to do back-to-back testing out in the field.
No, of course not. I'm just saying we need to be careful, and we need to take...
9.2.
So, theoretically, the horizontal speed will keep decreasing until the container hits the ground. The higher the drop altitude, the lower the horizontal speed at touchdown.
Sure.
But obviously, the higher the altitude, the higher the vertical speed, up to a certain point.
Absolutely. So, assuming the drop altitude's very low, the vertical speed won't be all that high on impact.
True.
And in terms of protecting the cargo, surely a low vertical speed is the critical factor.
I'm not so sure it's the critical factor. I'd say the horizontal speed's more problematic. Because, presumably, if the ground speed's quite high, there's a danger the container will roll over and bounce along when it touches down. In fact, if you're dropping from low altitude, that's probably inevitable. So if the container rolled and bounced for 50 meters or whatever, then you'd have to have some kind of destructible external envelope to protect it from the multiple impacts, which would be very expensive. So, arguably, rolling is the worst problem, worse than a high vertical impact speed.
You think so?
So, you don't think rolling's a bad thing?
I'm not convinced the container would actually roll.
No?
Not necessarily. The military drop tanks out of flying aircraft at low level, tied to special platforms, and they just slide along the ground.
Oh.
And the systems that eject things out of the backs of planes are incredibly powerful. So, because obviously they fire the container in the opposite direction to the plane, that reduces the ground speed. Plus, they use a parachute that deploys horizontally, which also helps to slow it down.
Of course.
So, based on what they do with tanks, I think we can safely assume that we can stop a container from rolling.
But a tank's got massive weight and a low center of gravity. With a smaller, lighter container, there's no way of knowing how it would behave, not without actually testing it. And even if you tested it 10 times, it would probably behave differently each time. It would be very unpredictable. Whereas, if you drop from a higher altitude, okay, the vertical speed is higher, but with a lower ground speed, it would behave more predictably. And that would make it easier to design a cushioning system, because you'd be dealing with a single predictable impact.
Yes, but surely a heavy vertical landing is a huge problem. The force of it would be far greater than...
9.3.
The first time we launched one of these things, we basically just got a plastic washing up liquid bottle, filled it about half full of water, then pumped it up with an ordinary foot pump.
So it was just ordinary household stuff?
Oh yeah, nothing too technical. And actually, there was a bit of a coincidence because the opening in the bottle was just slightly bigger than the fitting at the end of the pump, so there was quite a good seal. So we pumped it up, one of us held the bottle while someone else worked the pump. And we released it, and it went up literally like a rocket. I mean, we expected it would shoot up reasonably fast, but we didn't anticipate just how powerful it would be. It just went whoosh and totally exceeded our expectations. So you can imagine us, a group of 12-year-olds, we were absolutely ecstatic. And having said that, there was one problem. Once all the water had come out, which happened virtually in a split second, the bottle, because it was very light, started tumbling over in the air.
So it wouldn't fly straight?
That's right. But we quickly came up with a solution to that problem.
9.4.
What we did was to get a plastic cup, a strong one, not a disposable cup, and pushed it onto the end of the bottle at the top to form a nose. It didn't go exactly according to plan at first. It stabilized it a bit, but it still wasn't flying straight. So we tried putting water in the beaker to act as ballast, and that worked a treat. With the extra inertia and the fact that it was front-heavy, it went like an arrow. So yes, we sorted that problem out. Then the next goal was to increase the power to try and reach a higher altitude.
9.5.
One of the things we did was to experiment with the amount of water inside the bottle. I think initially we expected that the more water we put in, the more powerful it would be. But as it turned out, it was the opposite. What actually happened was, if you overfilled it, there wasn't enough pressure to expel all the water. We reduced the amount of water to about a quarter or a third full, something like that. And we also put some tape around the end of the pump to get a better seal with the bottle. That was really effective. I think we underestimated the pressure we were generating. And certainly we were overestimating the strength of the bottle, because it got to the point where we were firing these rockets up to, I don't know, maybe something like 20 meters high, something like that. So you can imagine the sort of pressure involved. And plastic bottles are hardly up to the job of high-pressure rocketry, obviously. So inevitably, the bottle eventually blew up while I was holding it. I was rolling around on the ground with sore hands while everyone else was rolling about laughing. So I learned the hard way.
9.6.
So how credible is this hoax theory then? I watched a documentary about it a while ago.
Well, some of the questions are quite interesting, but from what I've read, they can all be explained scientifically. You know, like the fact that the stars aren't visible in the sky on the photos. Apparently, it's just due to sunlight on the surface of the moon. It was too bright to see them, that's all.
Isn't the flag supposedly waving in the wind in one of the shots?
Yeah, that's right, yeah. They say it's because of the pole shaking after it had been stuck in. There's obviously no air, so as a result it kept moving for ages due to the fact that there was no friction to slow it down.
Oh, I see.
Another thing that's been explained is the footprints on the surface. People had said the ground looked wet, so it couldn't have been on the moon. But apparently that's the way that type of dust behaves in a vacuum. It sticks together like mud.
Wasn't there some other theory to do with dust when the module landed? That there should have been more dust or something?
Well, during the landing there was supposedly a lot of dust flying up, you know, caused by the blast from the engines. But when the module's actually seen on the surface, there's no crater visible below it. So the theory is that if it had really landed there, it would have left a crater. But the argument against that is that it had already slowed down substantially by the time it reached the surface, and it was only descending gently because of the low gravity.
Oh. So there was only a bit of surface dust blown up?
That's right.
Ngoại ngữ chuyên ngành.com